Okay, in this video we're going to talk about acid equilibrium. So the equation for a generic acid dissolving in water and ionizing what dissolves in water is as follows. So we've got my generic acid HA. It's going to react with water, and then I'm going to write this with an equilibrium arrow. That would be implying that this is a weak acid. If it was a strong acid, then I would just use a one-sided arrow, and then we have A minus and H3O plus. And I should put in the states. And so the equilibrium constant for this reaction is, and since this is a very specific type of equilibrium, we actually give it the subscript A to tell us this is an acid equilibrium constant, or an acid ionization constant. And so we would have the products over the reactants. And of course, because water is a liquid, it doesn't appear in our equilibrium constant expression. And so this Ka is called the acid ionization constant, and it represents the equilibrium for the reaction of the dissociation of an acid in water. All right, and so the magnitude of Ka tells us about the strength of the acid. Right, so the bigger the Ka is, the more products are favored at equilibrium, and so the stronger the acid is. And so strong acids, what differentiates them from weak acids is that they completely dissociate, right? Equilibrium lies essentially far to the right, right? Essentially lies all the way to the right. And so we assume that when we dissolve a strong acid in water, all of the HA is gone, and we only have H3O plus and H minus when that acid dissolves. Weak acids do not completely dissociate. We say they partially dissociate, and for all weak acids, equilibrium lies far to the left. All weak acids only partially dissociate, and often they dissociate only a very tiny amount. And so if you notice the difference when I wrote these two equations, if I know I have a strong acid, I use a one-sided arrow because I know that reaction is going to go to completion. If I'm writing this equation for a weak acid, I use the equilibrium arrows because I know those reactions don't go to completion, and I'm going to have significant amounts of the undissociated acid present at equilibrium. All right, and so just a reminder, how do you know if something is a strong acid? And I've gone ahead and thrown the strong bases in here. This is our list of 7 strong acids. You need to be sure that you have these memorized. I don't have any tips for memorizing them. You just maybe flashcards, but you need to know which acids we'll be considering strong. And then the strong bases, they're a little bit easier to remember because what we can do, the hydroxides of the alkali metals are all considered strong. And then among the hydroxides of the alkaline earth metals, calcium, barium, and strontium, all of those hydroxides are strong bases. And so when I draw it in like that, it kind of looks like a B, right? For base, those are our 8 strong bases. All right, and so we talked about this a second ago, but the size or the magnitude of Ka tells me about the strength of the acid. And so all of these are considered weak acids, but not all weak acids are created equally, right? If we have a larger Ka, while these are all weak acids, the ones that have larger Kas are stronger than the weak acids that have smaller Kas. And you can find Kas for strong acids, but often people don't use them. We don't report them because when we deal with a strong acid, we're not dealing with equilibrium problems. We're assuming that the reaction goes to completion, and so I don't need to worry about ice tables or anything like that when I'm dealing with strong acids. Okay, so we've talked about P functions before when we talked about pH and pOH, and the P function just said take the negative log of something. Because Ka's, and as we'll talk about a little bit later, Kb's are the base dissociation constant. These are often very small, and so it's often more convenient to report them as pKa's and pKb's, but the pKa is just the negative log of the Ka. The pKb is just the negative log of the Kb. Now, as we've been talking about, larger Ka's indicate stronger acids, but as Ka gets bigger, pKa actually gets smaller. So let's look at these two examples. I have chlorous acid and hydrocyanic acid, and because the Ka of chlorous acid is bigger than the Ka of hydrocyanic acid, we know that this is the stronger acid. Right? And let's compare their pKa's. So for chlorous acid, the pKa is negative log of 1.2 times 10 to the minus 2. And so that gives me a pKa of 1.92. And then for hydrocyanic acid, its pKa, negative log of 6.2 times 10 to the minus 10. And so that gives me a pKa of 9.21. Right, and so we can see, we already said this was the stronger acid, and so it has the smaller pKa. All right, and just like with pH and pOH, I can go back and forth between the hydronium ion concentration and the pH. I can go back and forth between the Ka and the pKa. So if I have the pKa and I want the Ka is just 10 to the minus pKa, or the Kb is just 10 to the minus pKb. Okay, so the last thing I want to mention on this slide is polyprotic acids. And so polyprotic acids are acids that have more than one hydrogen that they can donate. Now, for our purposes, we're not going to do a lot with polyprotic acids. If you go on to take analytical chemistry in particular, you'll deal with these a lot more. But for our purposes, polyprotic acids only donate their first proton. And if we look at this particular polyprotic acid, when it dissociates, so this is a weak acid, and so it only partially dissociates, and the first proton in a 0.1 molar solution creates 2.8 times 10 to the minus 3 molar H3O plus ions. The subsequent protons are always less acidic. And so not only are they less acidic, but because H3O plus has already been generated by the loss of the first proton, when we do an ice table, or based on Le Chatelier's principle, that's going to drive the equilibrium for the dissociation of the second proton to the left, and so the loss of the second proton only happens to a tiny amount, right? And so the second proton only contributes 10 to the minus 12 molar H3O plus. And so compared to the H3O plus produced by the first proton, right, this is truly insignificant. So for our purposes, when we deal with polyprotic acids, we only worry about the first proton coming off. The second proton doesn't dissociate appreciably at all. All right, so in the next slides, we'll look at how do we calculate the pH of strong acid and weak acid solutions.